support your defense. All right.
All right. Firstly, thanks for Dr. Pan's introduction. Hello, everyone. Today, I'm going to defend my dissertation, and the title is Towards Intelligent Mobile Aging, High Efficiency, Low Cost, and Good Decision. With the arrival of big data area, artificial intelligence has become one of the most disruptive technologies the world has been seen nowadays. And machine learning is a fundamental concept of AI research. Nowadays, when we bring the neural networks into the machine learning, we will have the deep learning, a powerful and efficient tool in both the academic and the industry fields. As we all know, AI has lots of interesting applications. For example, it shows strong ability in some computer vision or natural language processing tasks. Another example is AlphaGo. The machine can beat the smartest human in the Go game. And one of the main technologies of the AlphaGo is reinforcement learning. So such AI and deep learning techniques make our daily life better and more convenient. Another booming technology, mobile networks, has been attracted a lot of attention nowadays, from the widely used 3G or 4G network, which can support the message transmission or internet browsing, to the currently maturing 5G network, where we can download the movie in a few seconds, and then to the 6G and beyond in the near future. The accelerating data transmission speed and the increasingly flexible connection modes make the society move towards the area of Internet of all things. And in this process, there are lots of advanced technologies to support the 5G or 6G network. For example, the multi-access edge computing, which can bring the computing functions from cloud server to edge server and providing users with a reliable and low latency service experience. Another example is the device-to-device communication. It can establish the communication links between two devices directly without traversing the base station, which greatly improves the spectrum efficiency of the network. Mobile networks and AI, while each is individually revolutionizing industries and enabling new experience, there are still some problems to be solved for each one. And for AI, it still faces the challenges of how to scale the AI and how can we connect all participants and execute the training in a distributed manner. And for mobile networks, there still exists some wireless challenges, such as how to mitigate the interference between two devices, or how can we improve the spectrum efficiency. And fortunately, AI and mobile networks can help each other and solve their own difficulties. And the interaction between these two emerging technologies will derive a new nexus, that is the intelligent mobile aging, which coordinates these technologies to further develop both sides and correct new application scenarios. Specifically, the intelligent mobile aging can be illustrated in the following two perspectives. From wireless for AI, we can exploit mobile networks to better support AI. And from AI for wireless, we can apply AI to overcome some challenges in mobile networks. And in the following, let's see the details of these two perspectives. The first perspective is we can exploit mobile networks to better support AI. In the past, we know that most learning approaches are centralized, where both AI training and AI inference will be executed in the cloud. Currently, some mobile devices like the mobile phone are occupied with a powerful CPU or GPU, and it can take some inference tasks. We call it a partially distributed AI. In the near future, we will have this fully distributed AI architecture, where we can execute the computing tasks on mobile devices locally. So we have this federated learning over mobile edge devices architecture. And in this situation, the training is executed locally, and we can use the high-speed transmission process like the 5G to transmit the model between the base station and the mobile devices. However, the training efficiency needs to be solved urgently, because in this situation, the mobile devices are always battery supported and it can provide timely services. So the total energy or time consumption during the training process needs to be further reduced. Another perspective is we can apply AI to overcome some challenges in mobile networks. For some wireless challenges, it's difficult to solve them by the traditional methods. The first point is some problems are hard to model, especially with the dynamic communication environments. And the second point is for such nonlinear or non-convex problem, it's difficult to find the feasible solutions, and the computational complexity will be high. Luckily, for the above mentioned challenges, AI is a powerful tool to solve them due to its strengths. Firstly, because we introduce the neural network in deep learning, so it can easily represent any hard-to-model problems. And secondly, we can always find the near ideal solutions by some optimization methods like the stochastic gradient descent. And thirdly, after we train the model, we can avoid the computational complexity in the inference stage. So if we want to use the model, we only need to do some simple inference. And it should be noticed that when applying AI in mobile networks, the training performance is the focus and needs to be further investigated, where we want to find good wireless control strategies with fast learning performance and with fast learning convergence. So my dissertation topics focus on intelligent mobile aging, and I will introduce several works of my research related to the perspectives mentioned earlier. From AI for wireless, two thrusts related to time or energy efficient federated learning will be introduced, where we aim to finish the training tasks with the lowest cost. And from wireless for AI, I'm going to provide one thrust focusing on good D2D resource allocation decision with deep reinforcement learning approach, where the high training efficiency and good decision are our targets. So for thrust one, I have already introduced it in my proposal exam, so I will quickly go through it. The title of thrust one is to talk or to work dynamic batch sizes assisted time efficient federated learning over future mobile age devices. Federated learning is a distributed learning framework which can collaborate a lot of devices to train a unified global model. It requires all participants to take the local computing and then transmit its model updates to the server for global aggregation. And such training tasks have already had or has the potential to support many interesting applications like the Google Gboard or some health-related or financial-related applications. One of the key components of this architecture is the training time consumption, and it includes two parts, the communication part and the computing part. So for us, we focus on reducing the training time consumption during the federated learning training. In the literature, there are some pioneering works focusing on reducing the training time, like the localized GD or gradient compression methods. But all of these works focus on improving the communication efficiency, and they ignore the computing cost because they think the communication is the bottleneck in the training process. However, with the rapid development of wireless communications, the communication and computing is comparable nowadays. Let's take the ResNet 20 model on CFR10 dataset as an example. To transmit such a model by 5G links, we always require nearly 90 milliseconds. And to take one computing steps for such a model, we still need nearly 90 milliseconds. So the communication and computing is comparable these days. And by capturing such relationship, we are going to propose a time-efficient federated learning approach where we can fundamentally accelerate the training process. We also want to make a trade-off between the communication and computing to reduce the overall training time. And in this work, we are going to use the dynamic batch sizes technology to improve the training efficiency. It can save both the communication time and the computing time during the training process, since it requires less communication runs and it can enjoy the efficient large batch size training in the later training stage. So capturing the advantages of dynamic batch sizes, we are going to propose a dynamic batch sizes assisted federated learning algorithm. We call it DBFL. And here are some key steps of our proposed algorithm. For all devices, after receiving the global model, each device will select the batch size according to this equation. And in this equation, beta is the incremental factor and tau is the communication index. So the batch size will be exponentially or gradually increased during the training process. And after selecting the batch size, each device will execute the local computing with each steps. We call these techniques local SGD. And after proposing the DBFI algorithm, we are going to make a trade-off between the communication and computing to reduce the overall training time consumption. And we can achieve it by adjusting the incremental factor. And let's look at the formulation. The time consumption per device includes two parts, the communication part and the computing part. And for the communication part, the communication runs can be derived from the convergence analysis, and the communication cost per round can be calculated based on the Shannon equation. And for the computing cost, it equals to the sum of the computing cost in each round, which will be related to the memory frequency and the call frequency of the GPU. It will also be impacted by the batch sizes. And we further look into this time consumption formulation, and we can find that there is a trade-off between the communication and the computing by adjusting this incremental factor. For example, if we increase the incremental factor beta, the communication runs will decrease, which means the communication cost will decrease. But for the computing cost, the batch size in each round will increase. Therefore, the computing cost will increase. So there exists a trade-off between the communication time and the computing time by adjusting this incremental factor. For such training time minimization problem, we propose an iterative scheme to solve it. Firstly, since the objective is in a fractional form, which is difficult to solve, so in the first step, we use the Dinkelback method to reformulate the problem, and we treat it as the outer loop. And then we apply the NOVA algorithm to approximate the non-convex term in the reformulated problem, and we treat it as the inner loop. And finally, we will have our optimal results, that is the optimal incremental factor. Let's move to the performance evaluation part. We compare our algorithm with two baselines. The first one is the federated average. It's a typical federated learning algorithm where we gradually decrease the learning rate in the training process. And the other one is GIBS. It's another gradually increasing batch size approach without considering the local computing techniques. And we take the RetiNet 20 model on CFR10 dataset as an example. The first figure shows all three schemes have the same convergence rate in terms of the data epochs. And the second figure shows our proposed DBFI algorithm, the blue line, outperforms other approaches in terms of the training time consumption. And the similar results can be found on VGG19 model on CFR100 dataset. And finally, let me conclude my thrust one. And in this work, we propose a time-efficient federated learning algorithm that allows gradually increasing the batch size, where we can reduce both the communication and the computing time. And we also derive the convergence rate and the computational complexity of our proposed algorithm. And finally, we adjust the incremental factor to balance the communication and computing, thus minimizing the overall time consumption during the training process. That's the work one. Next, let's move to my second work, where we still focus on efficient federated learning training. And the title is Energy and Spectrum Efficient Federated Learning by High Precision Over-the-Air Computation. Over-the-air computation is a fast wireless data aggregation and the transmission process thanks to the superposition property of the transmission signal. air comp signals can be aggregated over the air, and we can directly receive the aggregated results. Unlike the traditional wireless data transmission process, where we need the orthogonal channels to transmit the data from different devices, air comp allows all devices to use the whole spectrum for transmissions simultaneously. For example, if we want to transmit 1, 2, 3, 3 different values from 3 different devices, and we want to get the aggregated results, for the traditional methods, we can use 3 different channels to transmit these 3 different values simultaneously, and then we can get the aggregated results. But for our over-the-air computation scheme, if we still want to transmit these 3 values, we can use 1 channel to transmit these 3 values simultaneously, and these 3 values can be aggregated over the air, and we can directly receive the aggregated results. So it can save the communication resources and improve the communication efficiency. Considering the communication efficiency advantage of air comp, recently there is a new architecture of the federated learning approach called air comp federated learning, where the over-the-air computation techniques is integrated into the federated learning approach. And the over-the-air computation is consistent with the federated learning process, since both of them focus on the aggregated results. And the local updates transmission process in federated learning can use the air comp to save the communication resources. In the literature, some works have focused on air comp federated learning. And however, there are still some limitations that need further investigation. Firstly, most of works apply the analog modulation scheme, which is not compatible with commercial devices, since current devices always occupied with a digital modulation module. And secondly, one pioneering works, they propose a 1-bit air comp approach. And as described in its name, the training precision is low. Thirdly, most works focus on 1 iteration performance of the federated learning, and the overall precision during the whole training procedure is overlooked. And lastly, most works don't consider the energy consumption issue, which is important for mobile devices. Therefore, we are going to propose a new air comp federated learning approach to tackle the limitations mentioned above, and the contributions are summarized here. For challenge 1 and challenge 2, we are going to propose a multi-bit digital modulation scheme, which can be compatible with commercial devices and provide high precision. And for challenge 3, we are going to derive a long-term convergence analysis. And lastly, we will consider the energy efficiency issue, which is important but not considered in previous works. Let's look at the air comp federated learning transmission model. The input of the air comp are local gradients calculated by each participating devices, and the outputs are the aggregated results received by the receiver. And these aggregated results can be calculated with this equation. And in this equation, H and P are channel coefficient and power control respectively. And this is a typical air comp transmission model. To make it compatible with commercial devices, we design a digital modulation scheme for the air comp transmission, as shown in this figure, and we call it multi-bit air comp or M-air comp. And in our design, firstly, each gradient is clipped and quantized as the MASK symbol, which is compatible with the modern digital devices. In the following, 2 MASK symbols can be transmitted orthogonally, and all devices will transmit the signal simultaneously. From the server side, the received signal can be waved from a higher order rectangular comp constellation, and then we assume each server will equipped with a high resolution ADC to convert the analog signal to digital values. And finally, we can obtain the aggregated results, and we call this scheme a multi-bit air comp. Let's look at the details of this transmission model. Since the channel coefficients are different among different devices, so we apply the power control policy to compensate the shift posed by channel that can make each user contribute equally as the receiver side. In other words, we hope the result of HK multiplied by BK are the same for all users. And in our model, we assume the device has the power budget. So the transmission power should be smaller than a specific value. And under this constraint, we propose a power control policy where we want to use the power control policy to compensate the channel shift. And here we set a channel threshold because the transmit power cannot be infinitely enlarged to meet the requirements. Therefore, the gradients with poor channel conditions cannot transmit it. And we can set this channel threshold by ourselves, and the minimum threshold value should be related to the power constraint. So according to this power control policy, the transmission process will only involve gradients with good channel conditions. Thus, we define a long-term average transmission probability to represent the participant probability of the gradients, and it can be calculated based on the channel distribution. And here we assume the channel coefficient is really distributed, and the achievable highest transmission probability can be determined by setting the channel threshold, setting the minimum channel threshold, which is calculated before. Next, we are going to propose an energy and spectrum efficient over-the-air federated learning algorithm. Let's look at the details of this procedure. Firstly, each device will execute each local computing steps, and then we can use the gradient quantization methods to quantize the gradients into a lower bit. And the gradients can be modulated into the digital symbol for multi-bit AirCom transmission. And for the multi-bit AirCom transmission, all gradients can be aggregated over the air with the threshold GTH. It should be noticed that we only transmit the gradients with good channel conditions. So the transmission probability is PB. And the final step is we can use the aggregated results to update the global model. And the aggregated results can be affected by both the AirComp operation and the quantization operation. Since in this paper, we focus on the energy consumption, and it includes two parts, the communication part and the computing part. For the communication part, we firstly calculate the average transmit power, which is related to the channel distribution. Since the channel coefficient is really distributed, so we can easily obtain the average transmit power by this equation. And in this equation, the EI is an exponential integrate function, and which can be bracketed by the elementary functions. And then we can get the closed form function of the average transmit power. And finally, we will have the energy consumption of the communication parts, which is equal to the transmit power times the transmit time. And for the computing parts, similar to the computing models proposed in previous work, we can calculate the computing power and the computing time, which are related to the GPU memory frequency and core frequency. And then we can calculate the computing energy consumption, which is equal to the computing power times the computing time. After having the communication and the computing energy models, we formulate the energy minimization problem shown in this equation. And the total energy consumption is equal to the product of communication rounds and the energy consumption per round. And we want to optimize the transmission probability PB and the local computing steps H to minimize the overall energy consumption. And for in this problem, the communication rounds can still be derived from the convergence analysis. Compared with the typical federated learning algorithm, our proposed ESOA-FI algorithm have one additional multi-bit AirComp operation. So we calculate the mean and the variance of this calculation. And based on this mean and variance, we can derive the convergence rate. And comparing with the typical federated learning convergence rate, we have one additional term, which is related to the transmission noise. And this convergence rate can also be affected by the transmission probability PB. So if we set the transmission noise equals to 0 and the transmission probability PB equals to 1, our proposed algorithm will converge to the typical federated learning algorithm, which shows the tightness and the effectiveness of our bound. And based on this convergence rate, we can derive the communication complexity, and the communication runs can be represented by this big O notation. For our optimization problem, we define the optimization variables PB and H as phi, and the optimization objective as capital theta. We also define the first function, the communication runs, as theta 1, and the second function, the energy consumption in each run, as theta 2. Since we cannot judge the convexity of the objective function, but luckily we found that both theta 1 function and theta 2 function are convex, and it has the product of convexity property. Therefore, we can apply the NOVA algorithm to linearize the non-convex term in the original function, and then we can iteratively solve the approximated problem and get the optimal results. Next, let's move to the performance evaluation part. We first implement our proposed multi-bit error comp transmission, as shown in this figure. The RTX server and one USRP are the aggregator, and the NVIDIA TX tools and the USRPs can be seen as the local devices. And in figure 2, the left two figures show the constellation of the transmitter, and the right figure shows the constellation of the receiver. So from the constellation, the receiving sample set is expanded into a constellation for higher order modulations, and the aggregated sample will be further decoded as quantized values. This demo shows the received sample can be easily decoded, which indicates the feasibility of multi-bit error comp. And let's move to the performance comparison of our proposed ESOA-FI algorithm. And here we consider 4 baselines. The first one is a federated average. It is a typical federated learning algorithm with ideal transmission. And the second one is a FET PAQ. It is a federated average algorithm with gradient quantization techniques to save the communication resources. And the third one is an advanced version of 1-bit error comp federated learning, where we integrate the local computing techniques into the OBDA algorithm. And finally is our proposed ESOA-FI algorithm with the maximum transmission probability. And we still use the ResNet 20 model on CFR10 dataset as an example. And these 2 figures shows the communication resources consumption and the energy consumption during the training process. And we can easily see that when achieving a target training loss or a target training accuracy, our proposed ESOA-FI algorithm consumes the latest communication resources and the energy consumption during the training process. And the similar observations can be found on a different dataset like the MNIST dataset on different non-ID settings and on different number of participating devices. Finally, let me conclude my second work. In this work, we propose a spectrum and energy efficient federated learning algorithm with high precision digital multi-bit error comp design, where we derive the convergence rate and the computational complexity of our method. And finally, we adjust the transmission probability and the local computing steps to minimize the overall energy consumption. After introducing 2 works related to wireless for AI, I'm going to move to my third work, which is related to AI for wireless. And the title is Make Smart Decisions Faster,
deciding D2D resource allocation by Starbrook game-guided multi-agent deep reinforcement learning. Device-to-device communication has emerged as a vital component for 5G cellular networks, and it allows two devices to transmit the data directly without traversing the base station. It has the potential to support some interesting applications like the content sharing or playing video games together. It can also improve the resource utilization and enhance user experience. Since the D2D link will reuse the spectrum of the cellular networks, it may cause the interference of cellular links. Thus, we need to consider the D2D resource allocation scheme, that is the channel allocation and power control, to mitigate the interference. And in this D2D communication problem, we always need to consider the dynamic environments, since users may change their locations and the channel is fading. Therefore, the channel conditions are changing over the time. In the literature, some works focus on this D2D resource allocation problem, but most of them are centralized optimization approaches, which is impractical because it's difficult to collect the full channel state information of these centralized approaches. Moreover, some works consider the game theoretical approach. And in the game theoretical approach, all players, like the D2D users or the base station, they negotiate with others and want to achieve an equilibrium. And for such game theoretical approach, although it can be executed in a distributed manner and we can always find the stable equilibrium, but these methods, they don't consider the time varying channel conditions. So if the environment is changed, we need to resolve the problem, and we need to solve the problem repeatedly. And nowadays, some papers apply the reinforcement learning algorithm to tackle this dynamic issue. As shown in this figure, in the multi-agent reinforcement learning problem, and in each state, the agent will take an action, and it will interact with the environments. The environments will give us a reward and let the agent move to the next state. So for this reinforcement learning approach, it can make the sequential decisions to tackle the dynamic issue. But for such problem, we always need a long time to converge. And by combining the advantages of game theoretical approach and the reinforcement learning approach, we are going to propose a game theory guided reinforcement learning approach, because we find the game theory approach and the reinforcement learning approach, they have the same goal. Both of them want to find a point that no one wants to change their behaviors or actions. And we find that the equilibrium in game theoretical approach equals to the optimal policy in reinforcement learning. So for our proposed game theory guided reinforcement learning approach, we can make sequential decisions to tackle the dynamic issues. This is the advantage of the learning scheme. And for our scheme, we have a faster convergence rate with better performance, thanks to the advantage of game theoretical approach. Let's look at some notations of our system model. And we consider there are M cellular users and N D2D pairs in our system. And I is the index of the cellular link, and G is the index of the D2D link. So XIG can represent the status of channel reusing. And we use PIC and PGD to represent the transmit power for cellular users and the D2D users respectively. And the G is the channel gain, and the G bar is the interference channel. So we can calculate the SINR and the channel capacity of cellular users and the D2D users respectively. And for each D2D link, we are going to determine which channel it will reuse and what is the proper transmit power, as and can maximize its channel capacity and minimize the interference to other users. We first consider a one-time slot scenario where the channel gain is fixed. And in this situation, we use the Starbrook game approach to solve it, and we can obtain the equilibrium in each time slot. And we further consider a dynamic environments where the channel gain and the interference channel is changing. And in this situation, we are going to propose a Starbuck game guided multi-agent deep reinforcement learning approach to make the sequential decisions. Note that the equilibrium in each time slot will guide the learning process in this dynamic environments. Let's first look at our Starbuck game model. And the Starbuck game is a type of the game theory which contains two types of users. The first one is a leader, which will move first, and the other one is the followers, which will move after the leader. And the goal of these players is they want to find an equilibrium that no one wants to change their behaviors. So in our D2D resource allocation problem, the base station is the leader. It will occupy all communication resources, and it will set the unit reuse price. And all D2D pairs can be treated as the followers. It will pay the reuse fee for the channel reusing. And it will also select the channel and transmit power to mitigate the interference or improve the channel capacity. Let's look at the leader firstly. The utility of the leader can be defined as the sum of the cellular users' channel capacity and the revenue obtained by the channel reusing. And the revenue part can be calculated as the unit reuse price times the interference caused by D2D users. And the goal of the leader is to maximize its utility function by setting the proper unit reuse price alpha. And for the followers, the utility function can be defined as the channel capacity minus the cost due to the interference. And since each D2D link needs to reuse the channel occupied by the cellular networks, and thus the D2D links needs to pay for that interference. And the goal of the followers is to maximize its utility function by setting the proper transmit power and the selected channels. And for these problems, we can use the typical Starbuck solution to solve it, and we can get the equilibrium in each time slot. And next, we want to use this equilibrium to guide the training process in dynamic environments. And let's look at our reinforcement learning model. And here we consider a multi-agent deep reinforcement learning approach, where each D2D pair is an agent. So for each agent, the global state contains all the environmental components, like all channel conditions, all interference, and the unit reuse price. And for the local agent, it cannot obtain all the complete channel state information immediately. It can only observe some information related to itself, and we define it as the local observation. The action can be defined as the transmit power and the selected channel. And for the reward function, the reward is the utility function of the D2D pair, which is equal to the channel capacity minus the reusing fee paid to the base station. So next, let's look at how to solve this multi-agent deep reinforcement learning problem. The goal of the reinforcement learning is to find optimal solution, optimal policy that can maximize the expected long-term accumulated reward. And it can be achieved by iteratively updating the value function, like the Q value defined in this equation. But in the Q value updating process, for each agent, we need to consider other agents' behavior, which will make the learning process difficult to converge. Therefore, we want to find a way to help the agent in the reinforcement learning training. And luckily, the goal of the game theory is consistent with the multi-agent reinforcement learning, where we want to find the strategy that no one wants to change their behaviors. So we want to use the game theory to guide the learning process. And the next step is how can we link them? And we find the Nash equilibrium in game theory equals to the optimal policy in multi-agent deep reinforcement learning. And for the optimal policy, it will satisfy this inequality, which is the same as the equilibrium in game theory. So based on these observations, we are going to propose a two-step learning procedure. The first step is we want to obtain the equilibrium from the Starbuck game module. And I have already introduced this part in previous slides. And the second step is we want to apply that equilibrium to update the components in reinforcement learning, like the value function and the policy. And for the original reinforcement learning problem, we always have a target value function. We can use this target value to update the policy and the value function. And this target value can be obtained from the existing action patterns. And for our proposed Starbuck game guided multi-agent deep reinforcement learning approach, we remove that target value function and proposed a Starbuck value, which can be obtained from the Starbuck module. So in the Q value updating process, we can use the Starbuck value to update the current Q value. And in this updating function, epsilon is the learning rate, and this Starbuck value, and this ST function is the Starbuck value, which can be calculated based on the Starbuck equilibrium. Therefore, in our proposed ST-DRI algorithm, and in each training step, we require additional calculations because we introduce the Starbuck game module. And this Starbuck game module will introduce additional information because we use the Starbuck equilibrium to guide the updating process. Therefore, from the overall perspective, our proposed algorithm will have a faster convergence rate and better performance because we introduce additional information in each step. Let's look at the overall procedure of our proposed ST-DRI algorithm. And we develop our algorithm based on MADDPG algorithm, a state-of-the-art multi-agent deep reinforcement learning approach. And for this approach, it contains two types of networks, the critic network and the actor network. And for the critic network, since we need the global state information and all agents' action to train this critic network, and it will be trained on the base station. And the loss function of the critic network can be defined as the distance between the target Starbuck value and our current Q value. And this target Starbuck value can be calculated based on the Starbuck equilibrium. So from this loss function, we can find that we can use the Starbuck equilibrium to guide the updating process of the reinforcement learning. And for the actor network, the goal of the network is to generate the action. Since we only need the local observations to generate the action, and then it will be trained locally. It will be trained on each D2D device. And the goal of the actor network is to generate the action that can maximize the value function. Therefore, the objective of the actor network can be defined as the value function directly, and we can optimize it by using the gradient ascent method. Let's turn to the performance evaluation part. We consider there are 4 cellular users and 4 D2D pairs in our system. And we consider the small scale feeding and large scale feeding in the simulation process. And here are some hyperparameters of our deep learning models. And we compare our algorithm with 3 baselines. The first one is a multi-agent deep reinforcement learning approach. And the second one is a single agent deep reinforcement learning approach. And the third one is the Starbuck game approach. And we treat it as the near optimal solution. And the first figure shows the average D2D pairs utility in a relatively static environment. And we find that our proposed approach, the blue line, converges faster and closer to the optimal Starbuck game approach. And the second figure shows the D2D utility distance between the Starbuck game and the learning schemes in a relatively dynamic environments. And in this setting, we change the large-scale feeding every episode. And from this figure, we can find that our proposed approach, the blue line, has a faster convergence rate with better performance compared with the typical multi-agent deep reinforcement learning approach. We further look at this table. This table shows the performance comparison of our proposed STDRL approach. We can see that for all of the D2D utility, D2D channel capacity, and the base station utility, our proposed scheme performs better than the typical MADRL approach. We also show the training time consumption for MADRL and the STDRL approach when they converge. And from this figure, we can find the proposed STDRL approach convergence in nearly 370 episodes, and the MADRL approach convergence in nearly about 500 episodes. So our proposed STDRL approach will save nearly 20% training time compared with the MADRL approach. This means when the environment dramatically changes and we need to retrain the model, our proposed method will converge faster. Finally, let me conclude my thrust 3. And in this work, we develop a Starbuck game-guided multi-agent deep reinforcement learning approach to enable the interference mitigated D2D resource allocation, where we apply the equilibrium obtained in the game theory module to guide the learning process, which can make our proposed algorithm convergence faster. And from the performance evaluation part, our simulation results show that our proposed algorithm outperforms the original MADRL approach in terms of the convergence time and the network performance. Finally, let me conclude my dissertation. And I focus on the intelligent mobile agent. And from wireless for AI perspective, I introduce 2 works related to efficient federated learning over mobile edge devices. And in one work, I integrate the dynamic batch sizes to save both the communication and the computing costs during the training. And in another work, I design a multi-bit error comp scheme to improve the spectrum efficiency. And in both 2 schemes, we make a trade-off between the communication and computing, thus minimizing the overall energy or time consumption. So in general, we propose 2 high-efficiency federated learning algorithms with low cost. And from AI for wireless, I propose a Starbuck game-guided multi-agent deep reinforcement learning approach for good D2D resource allocation. We apply the equilibrium obtained in the game theory module to guide the learning process, which can make our proposed algorithm convergence faster. And the simulation results show that our method outperforms the typical reinforcement learning approach in terms of the convergence time and network performance. So our method is high efficiency and can make good decisions. And for the future work, I may still focus on intelligent mobile agent. And one possible direction is we can apply the reinforcement learning to guide the federated learning process over mobile edge devices. When implementing the federated learning training in practical, there are still some challenges like the system heterogeneity, the stochastic runtime variance, or data heterogeneity. So if we want to take the optimal control for the federated learning training, we're considering all these challenges. The design space is massive and infeasible to enumerate. Therefore, we are going to apply the reinforcement learning based approach to let the agent automatically select the control strategies, such as the user selection or local computing steps control to improve the energy or time consumption during the training process. And here are my publications during the PhD study. And that's all for my dissertation. Thanks for your listening. Are there any questions?